We have seen how to apply this method, least squares method, for some experimental data. But the good explanation of this method should contain one more step. We should show or prove that these equations lead indeed to a minimum. You remember how to find a minimum. We compute the derivatives, we put them equal to 0 and we solve the system. But it is not yet sure that at this stationary point a minimum really occurs. It may be also a maximum or a saddle. How to be sure that this stationary point is indeed a minimum? The Hessian, the determinant of the matrix of second order derivatives. So let's consider the Hessian, which will be SAA, SAB, SBA, and SBB. So to consider the second derivative of S with respect to A, here we have the first derivative, and let's differentiate this once again with respect to A. Assuming xi and yi are constants. So we have 2 times sum, and when we expand this multiplication, that x times y is a constant as a function of a gives 0 in the derivative. X times b is a constant, but only axx, when differentiated with respect to a, gives xi squared. The mixed derivative can be obtained by considering this and differentiating with respect to b, or considering this and differentiate with respect to a, and the result is the same. If we differentiate this with respect to a, then we have sum, or we can factor out 2 times sum, and when we differentiate with respect to a, we have xi alone. The same here, if we differentiate with respect to b, then this times this gives bxi, and when differentiated with respect to b, we have xi. So 2 times sum xi. And finally, if we differentiate this with respect to b, then we have 2 times sum of 1, which is 2n. Well, in a general situation, if we have a function of 2 variables, then the derivatives are again functions of these 2 variables, a and b. A is here, b is here, a is here, b is here, but no a, no b in our result in the second derivatives. Where have we lost a and b? Well, if the function is quadratic in a and b, then the first derivatives are linear and the second derivatives are constant in a and b. So there is no a, no b, because the second derivative of a quadratic function is indeed a constant. We can factor out 2 from the first row, we can factor out 2 from the second row, and if we factor out n, that means we multiply by n and divide by n in the first row, then here we have x square bar, and here we have x bar alone. And if we do the same in the second row, that means we multiply and divide by n, we have x bar here, and we have just 1 here. Well, 4n squared is some positive constant, and we want the Hessian to be positive, so that the stationary point is not a saddle, but rather an extremum. 4 n squared, and here we have x squared bar times 1 minus x bar squared. Well, it would be nice if we are sure, if we can prove that this is always positive. To show this, consider the following computation. We have some values, x1, x2, x3, possibly more of them. Having these values, x1, x2, up to xn, we can consider the average, x bar. We had here some formula for the average. X bar is 1 over n, sum of xi, and I. Then we can subtract this average from every value here. Then we can consider the square of this difference. And we can consider the average of these squares of the differences. That means average means we sum and divide by n. And this can be written as x minus x bar squared, average of that. But if we perform this square, then we have x squared minus 2x x bar plus x bar squared and square of this, average of this. But average of sum is sum of averages, so we can write x squared bar minus 2, and 2 and x bar is a constant, and average of a constant times x is the constant times the average of x. So we have 2x bar, which is x bar squared, plus x bar squared, because average of a constant is a constant. But here we have the same expression with coefficients plus 1, minus 2. So the result is x squared bar minus x bar squared. You see? And this is exactly the expression that appears in this bracket. X squared average minus x average squared. Where does it come from? From here. It looks like it is positive, right? 1 over n is positive. Here we have squared, that means never negative, never negative. Is it indeed always positive? This is the average of some squares. It could be 0, right? In one very rare, very exceptional case, this can be 0 if all the brackets are equal to 0. Is this possible at all? Is it possible that each bracket, xi minus x bar, which means the average, is 0? This difference in 0 is if xi is equal to x average for every I. Can it happen that each number in this column is equal to the x bar, to the average? Yes, it is. If all the values are exactly the same, say 6, 6, 6, 6, 6, 6, 6 has the average of 6, and when you subtract the average, you have 0, 0, 0, 0, 0, 0, and when you average, or you take the square and average, you have 0. So the Hessian may be 0, but only in the stupid case when all the x values are the same. Well, but if all the x values are the same, we have no points like that. We have points that may be either just all the points are identical, if not just all x values are the same, but all y values are the same. And if y values differ, then we have some points like that. But it makes no sense to consider the least square method to fit these points with some line with this equation. So in practical applications, we have different values of x. And if at least two x values differ, then this is positive, this is positive, this n is positive, and there is no saddle, there is an extremum. Well, extremum may be minimum or maximum. Then we look at the diagonal elements, and if they are positive, and one is positive, this is positive, this is positive, so this will be indeed a minimum. So the algorithm of least square method does indeed find the minimum of this function, which is the sum of squares of the differences. And it is easy to compute and very practical. So this is a very, very common approach how to evaluate experimental data.